Hi students, this is Mr. Yao. Today we're going to talk about 10.2, where we will learn about independence and addition rule for probability. Sometimes we need to find the sample space for two or more events. So we have learned how to find a sample space for just one thing in the previous lesson. So for example, finding the sample space of all numbers from 1 through 7, we just write down 1, 2, 3, 4, 5, 6, 7. But this time we're going to do two events, and we're going to generate a sample space. So let's have a look at the first example. You roll a die and then flip a coin twice. Label 1 through 6 for the die, and H for heads, T for tails. It's asking what is the total number of outcomes, and also asks you to write out the sample space. So you see a box, you see a table on the right side. The first row is already filled out. These are the 1, 2, 3, 4, 5, 6, and these are the die. So they're the possibility of rolling a die. We're just separating them so that we can actually record what's going to happen when we flip the coin. So first, when we flip the coin, we can get one head and another head. And the rolling die is 1, so 1H8. That's just how we write to present it. We can also get the heads and then a tail. Or we can get a tail to begin with, a head. Then we can get tail and another tail. Now we might be wondering, well, the middle two are both just one head and one tail. Why do we write it twice? Well, because here the order actually matters. So getting the heads first and then tail, or getting the tail first and then head are actually going to be counted as different cases, or different elements. Now let's write it for 2. Same idea, 2, T, 2, TH, 2, T. We'll write it for all of them. H, 4HH, 5HH, 6HH, 3HT, 4HT, 5HT, 6HT, 3TH, 4TH, 5TH, 6TH, 3TT, 4TT, 5TT, and 6TT. If you count in total, we have 4 times 6, so 24 That's the number of outcomes. That's example 1. Now let's have a look at another example. This time we're rolling 2 dice. And it's asking the total number of outcomes. We're going to fill the sample space below again. So let's call this first row actually our first row. First row. And then let's call this vertical column our second row. So this space just means our first row is going to be a 1. Our second row is also going to be a 1. And in this space, our first row is still a 1, but our second row is actually a 2. Same thing, 1, 3, 1, 4, 1, 5, 1, 6. Next, 2, that's our first row. The second row is 1. So 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6. 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6. 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. We're not just writing like number 51, 52. That actually represents like 2 different rows. So in total, we have 36 total outcomes. Next, we're going to talk about compound events. Compound events is a combination of 2 or more simple events. When we say simple events, just like something that happens that's pretty easy to deal with, like rolling a die, or pick a red ball out of the bag, or just anything like that that is just simple, that's just dealing with one thing. And now we're actually going to be dealing with a compound event, so that means several of these little things happening, either at the same time, or they could be independent. Let's have a look. The union of A and B, it actually means A or B, because if you remember, the union actually is this symbol, which actually means A or B. It represents the addition rule, and here's how the addition rule works. That means the probability of 2 events is the sum of the probability that either will happen minus the probability that both will happen. Well, that sounds very mathematical. Let's actually look at the Venn diagram and see what it means. Let's say this side is the probability of A that's going to happen. This side is the B that's going to happen. We do see this middle part as the overlapping. So let's say we actually count the A. We counted that. Then we're going to count the B. You may actually notice the middle section, we actually counted twice. That's why we're going to do the A plus B and then minus whatever the overlapping part is. Because we counted twice, we're just going to need to get rid of one time. That's why we minus the probability that both will happen. Two events have nothing in common, and we call them mutually exclusive or disjoint. So that's the situation right here. If they don't actually share anything, there's no intersection, and we just call it mutually exclusive. As for the calculation, well, that just means this middle part that they share is actually a 0, which still just means A plus B. Now let's have a look at some examples. The key word is, again, union means or. Whenever we see the word or, we're just doing our addition rule. So if a six-sided die is rolled, what is the probability of rolling an even or prime number? Let's actually write them down. Even numbers, we have 2, 4, 6. Prime number, we have 2, 3, 5. If you don't remember prime number, these are the numbers that can only be divided by themselves and 1. These are prime numbers. So if you look at it, our P, roll, and even or prime, we need the total on the bottom. Since we're rolling a six-sided die, the total will be 6. The number that we need is probably even, these 3. And then we have prime would be these 2. We're not counting the 2 because we already counted it. So if you think about it, you can think it as this is the first part, that's 3 over 6, that's the even. We're going to add the prime number, which is another 3 over 6. Then we are going to subtract this number that actually repeated. Minus 1, 6 gives us 5 over 6. Next, part B. What is the probability of rolling a number less than 3? Roll less than 3. Let's think about it. Less than 3 would be 1, 2. Even number, 2, 4, 6. So P, roll less than 3 or even. Total would still be 6. First one, we got 1 and 2, so that's 2 out of 6. The second one, we got 2, 4, 6, that's 3 out of 6. Now let's see if we have anything that repeated. You can see this number 2 repeated, and we counted twice. And it's only one number that's repeating, so we minus 1 6. That's going to give us 4 over 6. Simplifies to 2/3. That's example 3. Example 4. A card is drawn from a deck of cards. What is the probability that the card drawn is a red or a heart? So P, red or heart. A red would be, let's think about how many red cards we have. The hearts are red and the diamonds are red. So we actually have 26 cards out of 52 that are red. Heart, we have 13 heart cards. Now we're going to get rid of the repetition. Let's think about it. We have some red cards are actually hearts. Actually, 13 of them, all the heart cards are actually red. Count them twice and subtract that. At the end, we got 26 over 52 simplifies to be 1 over 2. Next, probability of getting a diamond or spade. To get a diamond, we actually have 13 out of them again, 13 out of 52. As for spade, that's another 13 out of 52. Let's think about it. Can a diamond card actually be a spade? The answer is no. That's why there's no overlapping. So even if you want to subtract something, you're just going to subtract a 0, which we also don't need to write. Final answer, 1/2. That's example 4. Next, we have something called independence. Two events are considered independent if the probability of the first event has no impact on the probability of the second. And the example, draw a card and replace it before drawing another one. So this is the key, replace it. That means after you draw a card, you just put it back in the deck. So you still have 52 cards when you try to draw a card again. And these two, they do not affect each other. You may argue they do because it kind of matters where you put it. But in all randomization, we consider it to be not affecting each other. In order to calculate that, we are going to use the probability of event A, this time multiplied by the probability of event B. And here's another thing. In order to find a probability of, say, at least 1, we're actually going to do the opposite. At least 1 means, let's say we're trying to find all numbers up to 10 that are at least 1. That's quite a bit. So instead of thinking it that way, we find the complement. The complement in this case would be at most 1. The opposite of at least 1 would be like at most 1, and not even including 1. So we're going to calculate the probability of that, and then use 1 subtract. Because let's think about it. At most 1, well, that's actually very easy to calculate. If we don't include any negative numbers, that's just 0, and maybe 1, depending on how the question is saying. So that's way less than counting just all the numbers that's actually at least 1. So that's how we calculate the complement. Now let's have a look at some examples. This example only asks us to decide if an event or experiment is actually independent or not. So A, 1 card is drawn from each of the 2 decks. A red card is drawn from deck 1. Okay, deck 1. A face card is drawn from deck 2. Well, these are 2 completely different decks. And we can even try to draw cards from different at different places. And with different decks, they are for sure independent. Because they're not affecting each other. B, the daily traffic accidents in Hull involving pedal cyclist and motorcyclist. We actually consider motorcyclists to not be the same as a pedal cyclist. So they're not affecting each other because it says 3 motorcyclists are injured, then 1 pedalist are injured, cyclist is injured. They have no effect on each other. That's independent. Again. Part C. 2 boxes containing 20 nuts each. The nut picked out of the first box is BSF. Nut picked out of the second box is metrics. First box, second box, they do not affect each other. So independent. Okay, D. 1 box this time contains 20 nuts. First nut picked out of the box is BSF. Second is metric. So this time it is dependent. Reason? Well, because you are actually picking from the same box. After you pick out 1 from that box, you actually have less things left inside. So you're going to have a different probability when you try to pick out the second one. So it is being affected by the first pick. Now, another example, example 6. This time you can see the key word is actually and. So when we see the word and, we are going to multiply. 2 cards are drawn from a deck of cards with replacement. That means after you pick it, you are going to put it back. That's what with replacement means. What is the probability that the cards drawn are a diamond, P, diamond, and club? So picking a diamond, there's 13 of them out of 52. Then picking a club, that's another 13 out of 52. That's 1/4 times 1/4, which is 1/16. Next, a red card and spade. Red, there are 26 red cards, so 26 out of 52. And then for spade, we have 13 of them, so times 13 out of 52. And also because we are putting the cards back, that's why it's always out of 52 and they're not affecting each other. That's 1/2 times 1/4, which is 1/8. That's example 6. Last one, example 7. You draw a card out of the deck of cards. What is the probability that at least 1 is a heart? Well, we have 13 cards. If you actually want to do at least 1, you need to consider 1, 2 heart cards, 3 heart cards, 4 heart cards. That's going to make too many cases and so complicated. So instead, we're going to be dealing with the opposite. So that's the same as 1 minus P of at most 1 minus the probability of us drawing a card at most 1 heart. You are just drawing 1 card. So in this case, it's going to be 1 minus 52 is the total amount of cards, and the 1 heart, there are 13 of them, so it's 1 minus 4. But this actually doesn't make any difference because we're just drawing 1 card. Let's actually pretend we're drawing 2 cards. and think about what's going to happen. So if you're saying, I want at least one heart, that means we're having one heart or two hearts. So this time is going to be P minus 0 heart. Because think about it, if at least one heart, it means one heart or two hearts. Since you're just drawing two hearts, the opposite of that would just be you're not getting any heart. So 0 heart. 1 minus, if you're getting 0 heart for 2 picks, the first pick out of 52, you didn't pick any heart, that would be the other 39 cards. Second pick, same thing, put it back, so you got another 32 to actually consider the second pick. That's going to be 1 minus 3/4 times 3/4, which simplifies to be 1 minus 9/16, so 7/16. And this is actually more useful to calculate the complement. And that is everything for 10.2. Thank you.